Hello everyone, this video is about galvanic or voltaic cell. So galvanic cell is a cell that the reaction in it is spontaneous reaction. Therefore, the voltage of the cell is going to be a positive number. So these types of cells are always made from two separate containers with two electrodes on both sides connected through a wire. And usually we use a voltmeter to show the voltage of the cell. Now on each beaker, on each side, we'll have the electrolyte, which is the solution. So for this example, I'm using Ag solid and AgNO3 solution. And on the other side, I'm using Zn solid and ZnNO32 solution. So basically my electrode on the left-hand side is Ag solid. The electrolyte is made from Ag positive and NO3 minus. On the right-hand side, my electrode is Zn solid, and the ions inside the solution are Zn2 plus and NO3 minus. So as I said, this reaction has to be spontaneous. So the reaction that takes place between these two has to be spontaneous. So it's very important for us to pick the correct direction that each half reaction takes place in order for the overall reaction to be spontaneous. So for doing so, we have to take a look at the table like this one on the right-hand side, which is called the standard electrode potential. For this example, I'm using the IB data booklet basically for chemistry, but you can use any table that you like, doesn't matter as long as you have the reduction potential numbers for each one. The only thing you have to understand is the more positive this number is, the more that half reaction wants to be a reduction half reaction. And the less positive it is, the more it wants to be an oxidation half reaction. So if I compare the two values together, I can see that for Ag and Ag plus, this is my half reaction. And then for the other one is Zn and Zn2 plus. So this is going to be my half reaction. So basically, since the more positive number is for the Ag one, Ag positive is the one that's undergoing reduction. And then Zn and Zn2 plus, Zn is the one that's undergoing oxidation, basically. That's the only way the overall reaction is going to be spontaneous. So I'm going to be showing the half reactions over here. So as we said, for the oxidation half reaction, we're going to have Zn solid becoming Zn2 plus and losing 2 electrons. And then for the reduction, we're going to have Ag positive gaining an electron to becoming Ag solid. Now I'm going to also show the potential, the voltage of each of these half reactions. So for the reduction one, the number is always the same as it's written over here because all these numbers are based on reduction technically. So this is positive 0.80 volts. But then for the oxidation half reaction, we just have to flip the sign of that. So it's the negative 0.76 becomes now positive 0.76. And after this reaction takes place, the E of the cell, which is the overall voltage of this cell, is going to be found by adding the voltage of the oxidation and the reduction, which ends up being positive 1.56 volts. And the fact that it's a positive number shows us that the reaction is spontaneous. So that's what the voltmeter will show at the end of this reaction. However, keep in mind that this is the initial voltage of the cell. So meaning when the battery starts operating, that's how much voltage it has stored in it. But over time, your battery is going to die. So over time, you will notice that 1.56 keeps going down in number and eventually it will reach to 0. And that's when the equilibrium is reached and that's when the cell basically dies. Okay. Another thing we have to show is where anode and cathode is. So anode is the electrode that the oxidation takes place on it. So in this case, Zn is the one that gets oxidized. So this is going to be my anode. And then cathode is the site of reduction. So my cathode in this case would be Ag solid. Now the sign of anode and cathode are important. So for voltaic cells, anode always has a negative charge and cathode always has a positive charge. So I can put the negative over here, the positive over here. I'm sure when you look at a AA battery or a AAA battery, you've always seen the positive and negative signs on the battery. So which exactly shows the anode and cathode. Basically, you can tell which side the anode is and which side the cathode is. Now, another thing we have to show is the movement of electrons. So electrons always move from anode to the cathode through the wire. So this is the movement of electrons. The reason is because anode is the one that lost the electron, and then cathode is the one that wants to receive the electron. Okay, so our cell is pretty much finished. One last thing that we have to note is the accumulation of charge on both sides. Because if you look on the Zn side, Zn was the one that became Zn2 plus. So now what we have is an extra positive charge on the right-hand side. So basically what happened to the mass of our anode is the mass of anode went down because Zn solid from the anode turned into the solution. And then on the left-hand side, Ag plus from the solution went to become Ag solid. So the mass of our cathode went up and the concentration, the amount of positive ions on the left-hand side went down. So to avoid this accumulation of charge on both sides and to balance them, what these types of cells usually have is a salt bridge. So a salt bridge is like a U-tube glassware that kind of looks like this, that they fill it up with a solution similar to KNO3 or something similar. The reason I use KNO3 is because both K plus and NO3 minus are spectator ions, so they won't form a precipitate on either side. So it's a safe solution to put in there. So now what happens is that because now we have an excess of positive charge on the right-hand side, now NO3 minus can go to the right-hand side to balance that excess positive charge. And then on the left-hand side, we have a shortage of positive because we're losing the Ag positive. Therefore, K plus can go to the other side to balance that extra negative charge or the shortage of positive charge. But one thing about salt bridge is that the direction of the ion movement is not just going out of the salt bridge. Actually, ions can go through the salt bridge as well. So what can happen is because now on the right-hand side, we have an accumulation of positive charge on the right-hand side. So what can happen is Zn2 plus can also go through the salt bridge and make its way towards the cathode side. And then vice versa. Now on the left-hand side, we have extra, let's say, negative charge. So what can happen is that NO3 minus can also go through the salt bridge. Sorry, there's no room, so I'm trying to show it from the outside, but technically it goes through the salt bridge. So NO3 minus can also make its way towards the anode side. And this way, the charges are going to be balanced on both sides. Okay, so that was it for this video. I hope you enjoyed it. If you did, please make sure you like it and subscribe for watching more videos. Hope to see you in the next video.